The antiseptic smell of Toronto General Hospital couldn't mask the sweet, sickly odor that clung to Ward H like an invisible shroud. 14-year-old Elizabeth Hughes lay motionless in her narrow bed, her once bright eyes now sunken in a face that resembled aged parchment stretched over bone. At 75 pounds, she was slowly starving to death despite eating nothing but measured portions of whiskey, black coffee, and clear broth. Her breath carried the distinctive acetone scent that nurses recognized as the final warning before diabetic coma claimed another young life. Her parents sat vigil, holding hands worn smooth by months of desperate prayer. They had traveled from New York after exhausting every treatment, every specialist, every hope except one. In the same hospital, 3 floors below, a young orthopedic surgeon named Frederick Banting hunched over a medical journal, his calloused farmer's hands tracing the words of an obscure research article. He had no way of knowing that the idea forming in his mind would transform Elizabeth's death sentence into a miracle, or that his decision to value human life over personal profit would echo through history for generations to come. Frederick Grant Banting possessed the broad shoulders and steady hands of his farming ancestry, but his heart belonged to healing. Born in 1,891 inches, the rural Ontario community of Alliston, he grew up milking cows at dawn and watching his Methodist preacher grandfather tend to both souls and scraped knees with equal devotion. The Banting farm stretched across rolling hills where young Fred learned that hard work and moral character mattered more than social standing or inherited wealth. His path to medicine began with a childhood fascination with his father's veterinary treatments of sick livestock. Fred would hold animals still while his father administered medications, absorbing lessons about anatomy and compassion that no textbook could provide. When he announced his intention to study medicine at the University of Toronto, his practical father worried about the expense but recognized the determination in his son's eyes. The Great War interrupted Banting's medical studies in 19. He enlisted as a medical officer with the Canadian Army Medical Corps, serving in the muddy trenches of France where he learned to perform surgery under impossible conditions. At the Battle of Cambrai in 1917, shrapnel tore through his right arm, earning him the Military Cross for continuing to treat wounded soldiers despite his injuries. The war taught him that medicine was about more than textbooks and theory. It was about fighting death with whatever tools and knowledge you possessed. Returning to Toronto to complete his medical degree, Banting graduated in 1916 and specialized in orthopedic surgery, but establishing a practice proved more challenging than surviving combat. In July 1920, he opened his office in London, Ontario, hanging a modest shingle that announced his availability to treat the broken bones and joint problems of working-class families. His first month's earnings totaled exactly $4. The sparse waiting room and empty appointment book reflected a harsh reality that medical schools never taught. Being a competent surgeon meant nothing if patients couldn't afford your services or didn't trust an unknown young doctor with their care. Banting supplemented his meager income by teaching part-time at the University of Western Ontario. But financial pressures mounted daily. His medical practice was failing, his savings dwindling, and his future appeared increasingly uncertain. On October 30, 1920, while preparing a lecture on pancreatic function, Banting read an article by Moses Barron titled "The Relation of the Islets of Langerhans to Diabetes with Special Reference to Cases of Pancreatic Lithiasis." The dense medical language described how pancreatic duct blockages seemed to destroy the organ's digestive functions while preserving the mysterious islets of Langerhans. As Banting read deeper into the night, an idea began forming in his mind. What if those preserved islets held the key to treating diabetes? What if the internal secretion that researchers had theorized about for decades could finally be isolated and extracted? The failing country doctor had stumbled upon an idea that would change medical history forever. The imposing limestone facade of the University of Toronto's medical building seemed to mock Frederick Banting as he climbed the steps on a crisp November morning in 1920. His appointment with Professor John McLeod, the university's distinguished chair of physiology, represented either salvation for his struggling career or confirmation that his revolutionary idea was nothing more than wishful thinking by an inexperienced rural doctor. MacLeod's office reflected decades of academic achievement. Leather-bound medical journals lined mahogany shelves, while certificates and awards proclaimed his international reputation as an expert in carbohydrate metabolism and diabetes research. The Scottish-born professor had published extensively on diabetes, understood its devastating effects intimately, and had grown skeptical of ambitious young doctors who claimed to have solutions for medicine's most intractable problems. Banting sat nervously across from MacLeod's imposing desk, his farmer's hands fidgeting with his hat as he explained his theory. He proposed ligating the pancreatic ducts of dogs to destroy the organ's digestive functions while preserving the islets of Langerhans, then extracting the mysterious internal secretion that might control blood sugar. His voice carried the conviction of desperation, but his scientific credentials were virtually non-existent. MacLeod listened with the patience of a professor accustomed to enthusiastic but naive proposals from aspiring researchers. Diabetes had confounded medical science for centuries. Ancient physicians had recognized the disease's symptoms but possessed no understanding of its mechanisms or treatments. Modern researchers had theorized about pancreatic secretions that might regulate blood sugar, but countless attempts to isolate such substances had failed miserably. What could this orthopedic surgeon, with no research experience, possibly contribute to such a complex field? The meeting stretched through the morning as MacLeod systematically dissected Banting's proposal. The professor questioned his understanding of pancreatic anatomy, his knowledge of diabetes physiology, his familiarity with previous research failures, and his complete lack of laboratory experience. Each question revealed the vast gaps in Banting's scientific background while highlighting the ambition of his proposed research. Yet something in Banting's determination impressed MacLeod despite his reservations. The young doctor's passion was undeniable. His willingness to risk everything on an unproven theory spoke to a kind of courage that academic researchers sometimes lacked. Perhaps most importantly, Banting's outsider perspective might allow him to see possibilities that established experts had overlooked. After hours of discussion and cross-examination, MacLeod made a decision that would change medical history. He agreed to provide Banting with laboratory space for the summer months of 1921, along with a modest budget for experimental animals and basic supplies. He also assigned one of his best medical students, Charles Best, to assist with the research and ensure that proper scientific protocols were followed. As Banting left MacLeod's office that November day, he carried with him the opportunity he had desperately sought. But opportunity alone meant nothing without the knowledge, skill, and determination to transform his theory into reality. The real work was about to begin in a small laboratory where hope would battle against the accumulated failures of medical history. The summer heat of 1921 transformed the University of Toronto's physiology laboratory into a sweltering chamber of desperation and discovery. Frederick Banting and Charles Best arrived each morning before dawn, their shirts already damp with perspiration as they prepared for another day of experiments that teetered between breakthrough and catastrophe. The laboratory's concrete floors and bare walls offered no comfort, only the stark reality that they were attempting something that had defeated generations of researchers. Best, a 22-year-old medical student with sandy hair and an optimistic disposition, provided the scientific knowledge that Banting lacked. He understood laboratory procedures, could perform precise measurements, and possessed the steady hands necessary for delicate surgical procedures on their experimental animals. Their partnership represented the perfect fusion of desperate innovation and methodical expertise. Their first attempts to ligate pancreatic ducts in dogs produced mixed results that alternately encouraged and devastated them. The surgical procedure required precision that neither man had fully mastered, leading to infections that killed several animals before they could determine whether the treatment had preserved the crucial islets of Langerhans. Each failure represented not only wasted time and resources, but also the death of animals that had become familiar companions in their isolated laboratory. The physical demands of their work were brutal. They performed surgeries in stifling heat, monitored recovering animals around the clock, and tested blood sugar levels using primitive methods that required constant vigilance. Banting's savings dwindled as he lived on minimal food and rented the cheapest accommodations he could find. His medical practice in London had been abandoned completely, making this summer research his only chance for professional redemption. Their breakthrough came on July 27, 1921, when they successfully extracted pancreatic secretions from a dog whose ducts had been ligated weeks earlier. The islets of Langerhans had survived, while the organ's digestive functions had atrophied exactly as Banting had theorized. When they injected this crude extract into a diabetic dog named Marjorie, her blood sugar levels dropped dramatically within hours. Marjorie had been their most severely diabetic experimental animal, her condition so advanced that she could barely stand when they began their injection trials. The transformation was remarkable. Within hours of receiving the pancreatic extract, she showed increased energy and alertness. Blood tests confirmed that her glucose levels had normalized for the first time since they had induced her diabetes weeks earlier. The success was intoxicating but fragile. Their extract was crude and contained impurities that caused allergic reactions in some animals. The preparation process was inconsistent, producing batches that varied wildly in potency and purity. They had proven that the internal secretion existed and could lower blood sugar, but transforming this laboratory curiosity into a practical medical treatment would require expertise they didn't possess. Professor MacLeod returned from his summer vacation to find his laboratory transformed into a scene of controlled chaos. And Banting and Best had generated promising results, but their work lacked the scientific rigor and biochemical sophistication necessary for human trials. The next phase would require additional expertise, more resources, and the kind of systematic approach that could transform their crude extract into a medicine capable of saving human lives. The autumn of 1921 brought both hope and tension to the Toronto laboratory as biochemist James Collip joined Banting and Best's research team. Collip possessed the chemical expertise necessary to purify their crude pancreatic extract, but his arrival also meant that credit for the discovery would be shared among more contributors. Banting, who had conceived the original idea and risked everything to pursue it, watched nervously as academics with superior credentials began reshaping his vision. Collip's laboratory skills transformed their work from inspired amateurism into rigorous science. He developed sophisticated purification techniques that removed the toxic impurities responsible for allergic reactions, while concentrating the active principle that lowered blood sugar. His methodical approach contrasted sharply with Banting's intuitive leaps and Best's enthusiastic experimentation, creating productive friction that accelerated their progress. The team's success with diabetic dogs became increasingly consistent as Collip refined his purification methods. Animals that had been near death from induced diabetes returned to apparent health within hours of receiving injections. They gained weight, showed normal energy levels, and maintained stable blood sugar for extended periods. The laboratory that had been a place of desperate experimentation was becoming a factory for manufacturing miracles. Professor MacLeod assumed increasing control over the research program, insisting on proper documentation, statistical analysis, and scientific protocols that would satisfy the international medical community. His involvement was essential for legitimizing their work, but it also diluted Banting's role in what had originally been his personal quest. The country doctor who had conceived the breakthrough found himself becoming a junior partner in his own discovery. The naming of their extract reflected this collaborative dynamic. After considering various options, they settled on insulin from the Latin word insula, meaning island, in reference to the islets of Langerhans that produced the mysterious secretion. The name suggested a collective achievement rather than individual inspiration, much to Banting's frustration. Tensions within the team escalated as success brought increased attention from the medical community. Banting felt that his original contribution was being minimized while academics with better credentials received credit for ideas he had originated. Best worried that his essential role as co-researcher might be forgotten amid the politics of scientific recognition. Collip guarded his purification techniques jealously, concerned that others might claim credit for his chemical innovations. Despite these interpersonal conflicts, the science continued advancing at unprecedented speed. By December 1921, they had produced insulin preparations that were sufficiently pure and potent for human testing. Dogs that received their extract showed no adverse reactions while experiencing complete normalization of their diabetic symptoms. The laboratory results suggested that they had finally isolated the internal secretion that had eluded researchers for decades. The medical community began taking notice of reports emerging from Toronto. Diabetes specialists who had seen countless patients die despite their best efforts watched developments with cautious optimism. If the Toronto team had indeed discovered an effective treatment for diabetes, it would represent one of the most significant medical breakthroughs in history. But laboratory success with animals was only the first step. The ultimate test would require human subjects, and human lives hung in the balance. Leonard Thompson lay dying in Toronto General Hospital's diabetic ward, his 14-year-old body reduced to 65 pounds of skin stretched over prominent bones. His parents had brought him from their home in rural Ontario after local doctors pronounced his condition hopeless. Diabetes had stolen their son's childhood, replacing an active boy with a skeletal figure who drifted in and out of consciousness as his body consumed itself for fuel. Dr. Walter Campbell, the hospital's chief of medicine, understood that Leonard represented their last hope for testing insulin in humans. Traditional diabetes treatments had failed completely. The boy survived on a starvation diet that slowed his deterioration but offered no path to recovery. Without intervention, he would die within days, making him an ideal candidate for experimental treatment despite the unknown risks involved. On January 11, 1922, Frederick Banting prepared the first insulin injection intended for human use. His hands trembled slightly as he drew the clear liquid into the syringe, knowing that this moment would determine whether months of laboratory work would translate into a genuine medical breakthrough. Leonard Thompson would become the first human being to receive insulin treatment, making him either the beneficiary of a miracle cure or the victim of a tragic miscalculation. The initial injection produced disappointing results. Leonard developed a severe allergic reaction to impurities in the extract, his injection site becoming inflamed and painful while his blood sugar levels showed only modest improvement. The team's crude purification methods, adequate for animal experiments, proved insufficient for human treatment. Leonard's condition continued deteriorating despite their intervention, raising questions about whether insulin could ever be made safe for human use. James Collip worked frantically to refine his purification techniques while Leonard Thompson hovered near death. The biochemist understood that they had one more opportunity to prove insulin's effectiveness before losing their first human subject. His laboratory became a round-the-clock operation as he developed new methods for removing toxic impurities while preserving the extract's blood sugar-lowering properties. 12 days later, on January 23, 1922, Leonard Thompson received his second insulin injection using Collip's improved preparation. The transformation was immediate and dramatic. Within hours, his blood sugar levels dropped from dangerous heights to nearly normal ranges. His ketone production, the toxic byproduct of diabetic metabolism, virtually disappeared. Most remarkably, Leonard became alert and responsive for the first time in weeks. The medical staff who witnessed Leonard's recovery struggled to comprehend what they were seeing. Patients with advanced diabetes simply didn't recover spontaneously. The boy who had been unconscious and dying began sitting up in bed, asking for food, and showing interest in his surroundings. Blood tests confirmed that his metabolism had normalized in ways that medical science had never achieved before. News of Leonard Thompson's miraculous recovery spread quickly through Toronto General Hospital and beyond. Physicians who had treated diabetic patients for decades without seeing significant improvements suddenly had access to a treatment that seemed to reverse the disease's progression. The implications were staggering not just for Leonard, but for millions of diabetics worldwide who had been living under death sentences. Leonard's parents wept with gratitude as they watched their son return from the brink of death. The skeletal figure who had arrived at the hospital weeks earlier began gaining weight, strength, and the normal energy levels of a healthy teenager. Their family had been restored by a medical intervention that bordered on resurrection, made possible by a country doctor's desperate idea and a team's relentless pursuit of scientific truth. Toronto General Hospital's diabetic ward had earned its grim reputation as a place where families came to say goodbye. Ward H housed children and adults in various stages of diabetic deterioration, their beds arranged like stations on a journey toward inevitable death. Parents held vigil beside skeletal figures who bore little resemblance to the vibrant children they had once known. The ward's atmosphere reflected resignation rather than hope, as medical staff provided comfort rather than cure. The arrival of insulin transformed Ward H from a hospice into something approaching a resurrection center. Following Leonard Thompson's remarkable recovery, Dr. Campbell began treating other diabetic patients with carefully measured doses of the Toronto team's extract. Each injection represented an experiment in human salvation, as patients who had been abandoned by conventional medicine received their first real chance at survival. Teddy Ryder, age 5, had arrived from New Jersey weighing only 26 pounds. His parents had spent their life savings pursuing treatments that failed to slow his deterioration. When insulin injections began, Teddy's transformation rivaled Leonard Thompson's recovery. Within days, he showed increased appetite and energy. Within weeks, he had gained weight and begun playing with toys that had held no interest during his illness. Similar miracles occurred throughout the ward as insulin reached patients who had exhausted all other options. Adults who had been bedridden for months stood and walked. Children who had forgotten how to play rediscovered laughter and curiosity. Families who had prepared for funerals instead planned for futures they had never dared to imagine. The practical challenges of treating multiple patients revealed insulin's life-changing potential, while highlighting the enormous demand for this miraculous substance. Each patient required multiple daily injections, carefully timed with meals and adjusted based on blood sugar measurements. The nursing staff learned to recognize signs of insulin overdose, which could be as dangerous as untreated diabetes. Managing insulin therapy required precision and vigilance that transformed diabetes from an untreatable disease into a complex but manageable condition. Word of the Toronto miracles spread internationally through medical journals and newspaper reports. Desperate families from across North America and Europe began traveling to Toronto, hoping to secure insulin treatment for their diabetic relatives. The hospital's mail delivery included thousands of letters from parents, pleading for access to the drug that was saving lives in Ward H, while remaining unavailable elsewhere. The overwhelming demand revealed both insulin's incredible promise and the team's inability to meet global needs with their small-scale production methods. They had proven that diabetes could be controlled effectively, but manufacturing sufficient quantities for worldwide distribution would require resources and expertise far beyond their laboratory capabilities. Success had created a new problem, as millions of diabetics learned about a treatment they couldn't obtain. Dr. Elliot Joslin, America's leading diabetes specialist, visited Toronto to observe insulin treatments firsthand. His patients included some of the country's most prominent families, all of whom had lost children to diabetes despite access to the best medical care available. Joslin's endorsement of insulin therapy provided crucial validation from the international medical community, while highlighting the urgent need for mass production and distribution. The transformation of Ward H demonstrated insulin's potential to revolutionize diabetes treatment worldwide, but realizing that potential would require difficult decisions about manufacturing, distribution, and most importantly, who would control access to a treatment that represented the difference between life and death for millions of people. The Toronto team faced choices that would determine whether their discovery became a broadly accessible medical breakthrough or an expensive treatment available only to the wealthy. The magnitude of their achievement became clear to Frederick Banting and his colleagues as insulin's success attracted attention from pharmaceutical companies worldwide. Representatives from major drug manufacturers arrived in Toronto with briefcases full of contracts and promises of wealth beyond imagination. Eli Lilly and Company offered substantial royalties for exclusive North American rights, while European firms competed with equally generous proposals for international distribution agreements. Banting found himself facing a decision that would define not only his financial future but also his moral legacy. The patent for insulin production could make him one of the wealthiest doctors in history, providing financial security that would dwarf his struggles as a failing country practitioner. Commercial partners promised to handle manufacturing and distribution while paying the Toronto team percentage royalties on every dose sold to diabetic patients worldwide. Charles Best supported the commercialization approach, arguing that pharmaceutical companies possessed the resources and expertise necessary for large-scale insulin production. The demand for insulin far exceeded their laboratory's capacity, and patients were dying while waiting for access to treatment. Professional manufacturing would ensure quality control and widespread distribution more effectively than academic institutions could manage independently. James Collip advocated for protecting their intellectual property through strategic partnerships that would maintain scientific control while enabling commercial production. His chemical expertise had been crucial for developing purification methods that made insulin safe for human use. Licensing agreements could provide ongoing income, while ensuring that improvements to insulin preparation would continue under their guidance. Professor MacLeod approached the decision with academic caution, recognizing that commercialization decisions would affect the University of Toronto's reputation and relationships with other research institutions. The university had supported their work and deserved consideration in any agreements that generated substantial revenues. International patent protections would also preserve their priority for the discovery against competitors who might claim similar breakthroughs. But Banting struggled with a moral dilemma that kept him awake during long Toronto nights. He had witnessed firsthand the desperation of families who couldn't afford conventional diabetes treatments, watching parents exhaust their savings for ineffective remedies. Commercial control of insulin could create a situation where his discovery saved wealthy patients while remaining inaccessible to working-class families who needed it most. The team gathered in MacLeod's office on a gray February morning in 1922 to make their final decision. Legal documents lay spread across the mahogany desk, each contract representing millions of dollars in potential revenue. The decision would affect not only their personal finances, but also the future accessibility of insulin treatment for diabetic patients worldwide. Banting spoke first, his voice carrying the moral conviction that had sustained him through months of failed experiments and financial hardship. He proposed that they sell their insulin patents to the University of Toronto for the nominal sum of $1 each, ensuring that the institution could license production to multiple manufacturers, while preventing any single company from monopolizing this life-saving treatment. The room fell silent as his colleagues absorbed the implications of this proposal. They would surrender potentially unlimited wealth to ensure that insulin remained affordable and accessible to patients regardless of their economic circumstances. The decision reflected principles that placed human welfare above personal profit and establishing a precedent for medical research that prioritized public health over individual enrichment. One by one, Best, Collip, and MacLeod agreed to Banting's proposal. On May 3, 1922, they formally transferred their insulin patents to the University of Toronto for $1 each, creating a model for medical discoveries that would influence healthcare policy for generations. Their decision ensured that insulin would be available to any manufacturer willing to meet quality standards while paying reasonable licensing fees to support continued research. The telegram arrived at Frederick Banting's Toronto laboratory on October 25, 1923, its formal language barely containing the magnitude of its announcement. The Nobel Committee had awarded the prize in physiology or medicine to Banting and John MacLeod for their discovery of insulin, recognizing their achievement as one of the most significant medical breakthroughs in history. The country doctor who had struggled to earn $4 in his first month of practice had become the youngest recipient of medicine's highest honor. Banting's initial reaction was fury rather than celebration. The Nobel Committee had excluded Charles Best from the award, despite his essential role in every aspect of the insulin discovery. Best had been Banting's partner from the first crude experiments through the triumphant human trials, sharing the laboratory work, surgical procedures, and sleepless nights that had made their breakthrough possible. The omission seemed to Banting a profound injustice that diminished the collaborative nature of their achievement. The decision to honor MacLeod alongside Banting also rankled the primary discoverer. While MacLeod had provided laboratory space and scientific oversight, he had not originated the crucial insight about pancreatic duct ligation that had made insulin isolation possible. Banting felt that his own contributions were being diluted by sharing the prize with someone whose role had been more administrative than innovative. International recognition brought responsibilities that Banting found uncomfortable and unwelcome. Speaking invitations poured in from medical societies around the world, requesting presentations about insulin discovery and development. Publishers offered lucrative contracts for books about his research, while journalists sought interviews about his journey from failing practitioner to Nobel laureate. Fame proved to be a burden rather than a blessing for the modest doctor who preferred laboratory work to public attention. In a gesture that reflected his character and values, Banting announced that he would share his Nobel Prize money with Charles Best, recognizing his partner's contributions despite the committee's oversight. This decision shocked the medical community and demonstrated that Banting valued collaboration and fairness above personal recognition. MacLeod followed suit by sharing his portion of the prize with James Collip and ensuring that all 4 members of the Insulin team received some recognition for their contributions. The Nobel Prize ceremony in Stockholm provided a platform for Banting to address the international medical community about insulin's significance and potential. His acceptance speech emphasized the collaborative nature of medical research and the importance of making life-saving treatments accessible to patients regardless of their economic circumstances. He spoke about the dying children he had witnessed in diabetic wards and his conviction that medical discoveries belonged to humanity rather than to individual inventors. Global recognition of the insulin breakthrough accelerated research into diabetes treatment and prevention. Medical schools began incorporating endocrinology into their curricula, while hospitals established specialized diabetes clinics staffed by physicians trained in insulin therapy. The success of the Toronto team inspired other researchers to pursue equally ambitious projects, demonstrating that seemingly impossible medical challenges could be overcome through persistence and collaboration. Banting used his Nobel platform to advocate for accessible healthcare and continued medical research funding. He argued that governments and institutions had obligations to support scientific investigations that might benefit public health, even when immediate practical applications weren't apparent. His advocacy helped establish principles for medical research funding that emphasized social benefit rather than commercial potential. The recognition also brought increased scrutiny of Banting's decision to sell the insulin patents for $1 each. Some critics argued that he had sacrificed potential revenues that could have supported additional research projects. But supporters praised his commitment to ensuring insulin accessibility, noting that commercial monopolization might have limited the treatment to wealthy patients while leaving millions of diabetics without hope for survival. The success of insulin treatment in Toronto created an urgent global crisis, as millions of diabetic patients learned about a treatment they couldn't obtain. Letters poured into the University of Toronto from desperate families worldwide, begging for access to the drug that was saving lives in Ward H, while remaining unavailable elsewhere. The team's small laboratory could produce enough insulin for a few dozen patients, but global demand required industrial-scale manufacturing capabilities that exceeded their resources entirely. Eli Lilly and Company emerged as the primary partner for insulin mass production in North America. The Indianapolis-based pharmaceutical company possessed the manufacturing expertise, quality control systems, and distribution networks necessary for transforming the Toronto team's laboratory procedures into commercial operations. Company scientists worked closely with Collip to refine purification methods that could be scaled up for production of thousands of doses daily. The technical challenges of mass production proved as complex as the original discovery itself. Insulin extraction required fresh pancreases from cattle and pigs, necessitating partnerships with slaughterhouses and complex logistics for transporting raw materials before decomposition occurred. Each step in the purification process had to be standardized to ensure consistent potency and purity across different production batches. Quality control became a matter of life and death as insulin production expanded globally. Contaminated or incorrectly dosed preparations could kill patients as effectively as untreated diabetes, making rigorous testing procedures essential for every batch manufactured. The University of Toronto established standardization protocols that manufacturers worldwide were required to follow, ensuring that insulin produced in different countries maintained consistent therapeutic effectiveness. International distribution presented additional obstacles as insulin reached remote regions where diabetic patients had never imagined treatment might be possible. Refrigeration requirements complicated shipping to tropical climates, while customs, regulations, and import restrictions delayed deliveries to patients who measured survival in days rather than weeks. Medical missionaries and colonial administrators often became the primary distributors of insulin in regions lacking established healthcare infrastructure. The human impact of mass production became visible through individual stories of transformation and survival. Maria Santos, a diabetic teenager in rural Brazil, received her first insulin shipment through a missionary doctor who had read about the Toronto breakthrough. Her recovery from near death to normal health demonstrated insulin's universal effectiveness, regardless of geography or economic circumstances. Training programs for physicians and nurses expanded rapidly as insulin treatment spread globally. Medical professionals who had never encountered effective diabetes treatment needed education about injection techniques, dosage calculations, and recognition of insulin reactions. The University of Toronto became a pilgrimage destination for international medical visitors seeking expertise in diabetes management. Cost considerations remained paramount as Banting's dollar patent decision enabled competitive manufacturing by multiple companies. This competition kept insulin prices affordable for middle-class families while generating revenues for continued research and development. The contrast with other pharmaceutical products highlighted the benefits of Banting's decision to prioritize accessibility over profit maximization. Agricultural impacts emerged as insulin production consumed increasing quantities of animal pancreases. Beef and pork prices fluctuated based on insulin demand, while slaughterhouse operations adapted to accommodate pharmaceutical requirements for organ harvesting and preservation. Rural communities that supplied raw materials for insulin production became unexpected participants in the global fight against diabetes. Research continued into improved insulin preparations that would be longer lasting, more stable, or more easily administered. Scientists explored synthetic alternatives that might reduce dependence on animal sources while potentially improving therapeutic effectiveness. The success of natural insulin had created a foundation for ongoing innovation that would continue advancing diabetes treatment for decades. Frederick Banting's life after the Nobel Prize reflected his restless intellect and commitment to medical advancement beyond his insulin breakthrough. The recognition and financial security that came with his discovery provided freedom to pursue research interests that ranged from cancer investigation to aviation medicine. His laboratory at the University of Toronto became a hub for innovative medical research that tackled multiple diseases with the same systematic approach that had yielded insulin. World War II presented new opportunities for Banting to serve his country through medical research rather than battlefield surgery. The Royal Canadian Air Force recognized that high-altitude flying created physiological challenges that required scientific investigation to protect aircrew safety. Banting accepted responsibility for developing medical protocols that would enable pilots to operate effectively at altitudes where reduced oxygen pressure threatened consciousness and performance. His aviation medicine research proved as methodical and groundbreaking as his diabetes work had been 2 decades earlier. Banting subjected himself to altitude chamber experiments, experiencing firsthand the effects of oxygen deprivation and rapid decompression that military pilots faced in combat. His studies contributed to development of oxygen masks, pressure suits, and medical protocols that saved countless airmen's lives during the war. The transition from laboratory researcher to military consultant suited Banting's personality and patriotic convictions. He had served as a medical officer during World War I and understood the importance of applying scientific knowledge to protect military personnel. His reputation as the insulin discoverer provided credibility that ensured his aviation medicine recommendations received serious consideration from military leadership. Personal relationships remained important to Banting despite his professional demands and public recognition. He married Marion Robertson in 1924, though their union proved troubled by his devotion to research and uncomfortable relationship with celebrity status. Their divorce in 1932 reflected the challenges that many dedicated scientists face in balancing personal relationships with professional obsessions. His second marriage to Henrietta Ball in 1939 provided greater stability and happiness during his later years. Henrietta understood and supported his research commitments while providing the domestic peace that enabled him to focus on scientific work. Their relationship demonstrated that personal fulfillment was possible even for someone whose career demanded extraordinary dedication and sacrifice. Banting's growing frustration with medical commercialization became apparent as he witnessed healthcare becoming increasingly expensive and inaccessible to working-class families. Despite his decision to sell the insulin patent for $1, he observed pharmaceutical companies developing business models that prioritized profit margins over patient welfare. His speeches and writings increasingly emphasized the moral obligations that medical professionals had to serve human needs rather than commercial interests. Social activism became more prominent in Banting's later years as he advocated for universal health care and continued government support for medical research. He argued that insulin's success demonstrated the potential benefits of publicly funded scientific investigation, suggesting that similar approaches might yield breakthrough treatments for cancer, heart disease, and other major health challenges. The outbreak of World War II reinvigorated Banting's sense of purpose as he applied his scientific expertise to protecting military personnel. His aviation medicine research represented a natural evolution from his insulin work, demonstrating how medical science could address diverse challenges through careful observation, systematic experimentation, and practical application of discoveries. Tragedy struck on February 21, 1941, when the military aircraft carrying Banting to England for aviation medicine consultations crashed in Newfoundland during a severe storm. The man who had extended millions of lives through his insulin discovery died at age 49, his own life cut short while serving his country's war effort. His death represented not only personal loss for family and colleagues, but also the premature end of a scientific career that might have produced additional medical breakthroughs. Maria Rodriguez adjusted her continuous glucose monitor as she prepared for the Olympic 400-meter finals, the device barely visible beneath her team uniform. 2 quick insulin injections, precisely calculated for her pre-race nutrition, completed preparations that transformed what had once been a death sentence into a minor inconvenience. As she exploded from the starting blocks, her diabetic metabolism functioned as efficiently as any competitor's, thanks to the medical miracle that Frederick Banting had chosen to give away rather than exploit. The stadium erupted as Maria crossed the finish line victorious, her achievement representing not just personal triumph but the enduring power of accessible medicine. Her success stood as testimony to a country doctor's moral choice made in a Toronto laboratory over a century ago, when he decided that saving lives mattered more than personal wealth. Banting's decision to sell the insulin patent for $1 established a precedent that continues challenging modern medical economics. As pharmaceutical companies develop increasingly expensive treatments, his example raises uncomfortable questions about balancing innovation with accessibility. The man who could have become history's wealthiest doctor instead chose to ensure that his discovery would serve humanity rather than enrich himself. In hospital wards across the globe, diabetic children receive insulin injections that trace their lineage directly to Banting's laboratory and his moral courage. His legacy lives not in monuments or wealth, but in the countless lives extended and dreams fulfilled by those who might otherwise have perished. The miracle he sold for $1 continues saving lives daily, proving that the greatest medical breakthroughs serve humanity best when they remain accessible to all who need them.